Welcome to this edition of Coffee Cats. In this series, we're going to cover an introduction to soil testing and soil fertility. In this installment, we're going to define soil fertility. When we define essential elements, I like to refer to the definition provided by Haviland in his textbook, where a nutrient is considered essential if it meets three criteria. First, the element is directly involved in the nutrition of the plant. So it's involved in metabolic processes. A deficiency in the nutrient makes it impossible for the plant to complete its life cycle, and a deficiency is specific to that element can only be corrected by supplying that element. So adding some sort of other amendment won't correct this deficiency. There are two main groups of essential elements: the macronutrients, split into primary and secondary, and the micronutrients. And the macronutrients are required in the largest amount by the plants, and we typically just worry about the primary macronutrients when it comes to adding fertilizer. That's nitrogen, phosphorus, and potassium, because the soils typically can't supply enough of that nutrient to meet the crop's needs. Whereas with the secondary macronutrients, our normal ag soils provide plenty of these, especially here in Kentucky: calcium, magnesium, and sulfur. So we don't typically have to worry about adding those with fertilizer. When it comes to the micronutrients, if we're managing pH and if everything's okay with the crop environment, we rarely have to worry about adding these in a fertilizer, because the plants require so little of this nutrient and the soils typically supply enough. When we're describing the nutrient status of plants, we typically refer to the deficient, sufficient, or toxic or excessive status of a nutrient. And so if we look at this figure, we see that what we're talking about is these kind of three parts of this curve, where plant performance is on the vertical axis and nutrient concentration in the tissue is on the horizontal axis. And so as nutrient concentration in the plant increases, the deficiency becomes less severe as we approach that critical range or critical concentration, which is the break point between deficient and sufficient. Once a plant is sufficient in a nutrient, adding additional nutrients to the plant will not increase plant performance. And in fact, at some point, plant performance may begin to decline, specifically with the micronutrients, where toxicity is a problem. So deficiency, as we add more of a nutrient, plant performance increases. Sufficiency, plant performance doesn't change as we add the nutrient. And toxicity, plant performance declines as we add more of that nutrient. When we talk about soil fertility, we also have to talk about soil productivity. There's an old adage that says a productive soil is fertile, but a fertile soil is not always productive. And what this means is there's a lot of other things that control how much yield we get or how healthy our plants are. Plant nutrition isn't the only factor that affects plant growth. And in fact, these other factors can interact with plant nutrition and mask nutrient response or nutrient need. Most importantly is moisture. When we're in a drought, plants won't respond to fertilizer because they need water, so low fertility has no effect. Plants stand, putting the seed in the right place, having good seed-to-soil contact or good soil structure. If the soil is compacted, yield's going to be limited, and you can add all the fertilizer in the world, but that soil won't be productive. So soil fertility is not the only part of this equation. So when we talk about a soil's productivity and its ability to store and supply nutrients, this goes hand in hand with soil fertility. So there's kind of two pools of nutrients in the soil. There's the quantity and the intensity. So the quantity is the total amount of nutrient. Now, not all of that is plant available. It's stored in long-term pools like soil minerals, medium-term pools that relatively over a year might provide some nutrients like the organic matter, and then immediately available nutrients that are exchangeable, cations or on the soil colloids, and what's in the soil solution. Because remember, plants can only take up nutrients from the soil solution, so that nutrient has to be dissolved in the soil solution. And so as nutrients move to the soil solution, they're moving from this quantity or stored portion to this immediately available portion that we call the intensity. And so the relationship between the quantity, the total amount of nutrient present, and intensity, the amount that is available, or we call it labile, is the relationship that really controls soil fertility and what we try and get at with soil testing. And we'll talk more about that later. So one of the most important characteristics about soil when it comes to soil fertility is that soil structure. And soil structure has to do with those components of the soil. Now, the ideal soil is often considered to be half something and half nothing. And so that something is a mix of organic matter and mineral soil. In our soils, that's going to be about 2 to 5% organic matter. The rest, that mineral soil, which I think we most often think about as being soil. But soil also includes that pore space. So half of the soil should not have that solid material. It should be water and air. And really the ideal soil, that pore space, will only be half filled with water. More than that, and it's too saturated. So what do you think is the most important part of this ideal soil when it comes to the solid material, the water, and the air? I think a lot of people are surprised to find out that pore space is the most important part from our perspective as soil managers, because when we compact a soil, if we look at this figure here, we see that if we compact a soil, we run over it with heavy equipment when it's wet, we basically squeeze out that air. And then there's less pore space for air, which is essential for root respiration and for nutrient exchange. And then we end up with a really compacted soil that roots can't penetrate. It's saturated, so it's soggy, so the roots can't breathe. And so having that pore space, maintaining it at 50% of the soil, really gives us the best soil structure, because that's where the magic happens, as the roots can penetrate and expand and grow through that soil, and there's room for that nutrient exchange on the root surface. So let's wrap things up by talking about the 4 R's of nutrient management. The 4 R's are applying the right source in the right rate at the right time in the right place. But we've got to remember that it's not just how, where, when, and what fertilizer we apply, but we've got to do this in a well-managed cropping system, because again, a productive soil is always fertile, but a fertile soil is not always productive. So we've got to make sure that that cropping system is well managed. We've got to know what our performance objective is, because in row crop production, economic optimum yield, maximum yield, and the environmentally correct amount of nutrients may all be in competition. And so we're balancing performance objectives with yield, trying to maximize that yield, but also maximize profitability, and those are 2 different things, and also protecting the environment. If you're not in a cropping system, maybe you're producing forage or hay crop, or maybe you're a homeowner and you are worried about aesthetics and producing ornamental plants. These objectives directly control what the right rate is, the right source, the right placement, and the right timing of fertilizer application. So in summary, essential elements are those required for a plant to complete its life cycle and for metabolic processes. Deficiency symptoms can only be corrected by application of that element. Nutritional status can be described as deficient, sufficient, or excessive. Also toxic. If a plant is deficient, plant performance will improve with the addition of that element, and that results in increased tissue concentration. Soil fertility and nutrient management is management of the nutrients and growing environment to allow sufficient uptake of essential elements.